Hello everyone, and welcome back to The Explainer. Behind all those massive, mind-blowing headlines of today's generative AI boom is actually a very specific, incredibly powerful engine driving the whole thing. And today, we're going to uncover exactly what that engine is, minus all the confusing jargon. Okay, let's dive into this and completely demystify the tech that is literally reshaping our world. Transformers.
To guide us through this, we've got a really clear 5-step roadmap. First up, the Transformer revolution. 2, breaking it down into composites. 3, what can Transformers do? 4, opening the box to look at embeddings. And finally, number 5, the real secret sauce here, the magic of attention.
So, let's hit section 1, the Transformer revolution, and look at just how amazingly fast we've evolved. If we rewind back to the 1990s, well, we were basically in the prehistoric era of AI language models. We were heavily relying on rigid, rule-based methods and architectures like RNNs and LSTMs. Fast forward to 2014, and we start seeing these simple attention mechanisms pop up. But the absolute earthquake? That happened in 2017. A landmark paper dropped called Attention is All You Need, and it introduced the transformer architecture for natural language processing. I mean, this single breakthrough literally sparked an explosion, leading us right into the generative era kicking off around 2021. And obviously, that's the era we're living in right now, the era of ChatGPT, Dolly, and all those massive tools dominating the news cycle.
Moving right along to section 2, breaking it down. Let's talk about composites.
The absolute core concept we need to grasp first is the composite. By definition, a composite is simply something made up of distinct parts or elements. And in the world of Transformers, you have to remember absolutely everything is a composite. Text, that's just a composite of letters and words. Images are composites of pixels. Sound is just a composite of acoustic frames over time. Before a transformer can even begin to do its magic, it first has to break our messy reality down into these distinct, easily digestible parts.
It's kind of like a giant puzzle. Take a look here. We have a simple sentence. The elements of a sentence are words. Now, to actually process this, the machine chops the text into distinct puzzle pieces. We call these individual pieces tokens, and you guessed it, the process of chopping them up is called tokenization. A token could be a whole word, or sometimes it's just a small chunk of a word.
And this brilliantly illustrates that the exact same logic applies to visuals too. Look at this image of a fish. Instead of reading it as one giant, continuous picture, the tokenization process comes in and chops the image into distinct visual patches. Those little puzzle piece patches, they're the exact visual equivalent of the word tokens we were just talking about. So whether we're feeding it an article or a photograph, the transformer always begins by breaking that composite down into a collection of tokens. Okay, section 3. What transformers do. Let's take a look outside the box before we look inside.
The first major task they handle is classifying composites. Basically, we give the model a composite and ask it to predict a specific class. So, for instance, if we feed it an image of a cat sitting out in a field, the model processes all those little patches and spits out a prediction. It identifies the image as an Egyptian cat with a super high confidence score, clearly distinguishing it from, say, a tabby or a tiger cat.
Now, the second major task is completing composites. Imagine we have a sentence with a missing token, something like, "The blank barked at me." The model looks at all the surrounding tokens and has to figure out the most reasonable missing piece. Right here, a film mask model correctly guesses that the missing word is most likely wolf or dog. It's essentially predicting the future based on the past and present. Pretty cool, right? And then we have the third major task, which is probably the most famous one right now. Transforming composites entirely. This is where we literally cross from one medium into a totally different one. We can drop in a text prompt like, "A city above clouds, pastel colors, Victorian style," and a text-to-image model will just completely transform those text tokens into a brand new composite. Boom, a highly detailed image that matches exactly what we asked for. So we've seen the inputs, and we've seen the incredible outputs. But this brings us to the most important question of this entire explainer. How do transformers build representations? I mean, how exactly are they building these semantic representations of composites to pull off these incredible feats? Well, let's find out.
Section 4. Opening the box. It's time to understand embeddings.
We all know that computers don't natively speak English, right? Nor do they intrinsically understand what a fish looks like. For a machine to actually work with our tokens, it has to translate them into the only language it really knows, math. So we represent each and every single token as a vector of real numbers. Let's just call the number of dimensions d. This absolutely crucial translation step, taking a puzzle piece token and turning it into a mathematical vector, is what we call embedding.
But wait, here is where we hit a massive roadblock. A basic, static embedding, it just isn't enough. So the crucial point is this. In any composite, the meaning of a single token depends entirely on the other tokens around it. Think about the word bark. Are we talking about the rough outer layer of a tree or the loud sound a dog makes? The token for bark is mathematically identical in both cases. Its true meaning can only be unlocked by understanding its context within the broader sentence.
Which brings us perfectly to our final section, Section 5, the magic of attention. This is how we solve for context.
To really get this, I want you to imagine a crowded cocktail party where every single token is a guest. Here's how the attention mechanism works in 3 dynamic steps. Step 1, every token at the party sends out a message to every other token in the room. Step 2, each token actively listens to the room and computes just how much importance it wants to place on the messages from those other tokens, like, hey, are you relevant to me? And then step 3, based on that weighted attention, each token actually moves away from its original embedding. It shifts its mathematical direction to incorporate the meaning of the tokens it's paying attention to. So our bark token talks to the dog token across the room, realizes what's going on, and dynamically changes its own mathematical meaning to align with the animal, not the tree. It is literally context-aware embedding happening in real time.
And that leaves us with a truly fascinating, almost philosophical thought to end on. By allowing these tokens to talk to each other, to weigh each other's importance, and to dynamically shift their own fundamental definitions based on their surroundings, transformers have basically cracked the code of context. If the meaning of a single token depends entirely on its context, and our machines are now flawlessly mapping that contextual web mathematically, are machines finally learning to actually understand our world the way humans do? It's a profound question, and for sure, it's one that the next generation of generative AI is going to continue pushing to the absolute limits. Thank you so much for joining me for this explainer. I really hope this helped demystify the incredible engine that's powering our future.